Today, we are taking probably one of the biggest leaps in modern technology. We're journeying into brain-computer interfaces, or BCIs.
And this is a field that has just rocketed out of science fiction. I mean, it's landed squarely in this highly competitive, very regulated, very real medical space.
It really is the ultimate crossroad. And for the people who are counting on this technology, the stakes just could not be higher.
Absolutely. We are talking about devices that promise to restore something so fundamental: communication, mobility, for millions of people.
And the scale is just staggering.
It is. Our sources estimate there are about 5.4 million individuals just in the U.S. alone living with severe paralysis who could potentially benefit from this.
That's the mission. But the real story, the conflict that's defining this whole industry right now, is how you actually get there.
Right. And our sources really light up these two radically different philosophies that are in direct competition.
On one side, you have the high-risk, high-reward strategy, the Moonshot, and that's being spearheaded by Neuralink.
Yep. And on the other, you have this much more cautious, clinically proven approach, the pragmatic play, which is led by a company called Synchron.
So this is much more than just a tech race, isn't it?
Yeah.
It's a huge debate for regulators, for investors, and most of all for the patients.
Exactly. And the central question that's going to define the future of neurotech is really this: is it better to go all in for maximum performance? Aim for this high bandwidth, almost superhuman level of interaction.
Even if that means you need this incredibly invasive, expensive, and technically really difficult neurosurgery.
Or is the smarter path, the more scalable path, to prioritize safety above all else? Minimal invasiveness, getting to market quickly.
Even if that means, you're accepting a lower performance benchmark at the start.
And if you look at the evidence our sources are presenting, that second strategy has carved out a massive clinical advantage. Synchron has achieved what the industry calls translational maturity. I mean, they're the only company that has publicly reported long-term human implantation, we're talking over 12 months, without drilling a hole in someone's skull.
So without a craniotomy.
Without a craniotomy.
Right.
And clearing that safety and longevity hurdle, that is a colossal step. It gives them a much, much clearer path to a regulatory approval and eventually to market.
That's stability. Seems like that's the new gold standard. Okay, let's unpack this. Let's define exactly what these two radically different paths really look like.
So despite their wildly different methods, both Neuralink and Synchron, they start at the same place. They share this common goal of accessing the motor signal.
Right. They're essentially trying to intercept that cortical activity that's generated when you just think about moving, that silent signal in a paralyzed patient's brain.
Exactly. And once they capture that signal from the motor cortex, they use these really sophisticated decoding algorithms, which are heavily reliant on AI, by the way, to bypass the injured limbs and translate that thought directly into a command for a computer.
Okay, so let's start with the one that's gotten all the headlines. Neuralink. Path 1, the intercortical moonshot.
This approach is all about one thing: signal quality. Sheer data bandwidth above everything else.
And to get that quality, you have to be incredibly invasive. I mean, how drastic is the procedure they're asking patients to go through?
We are talking about a full craniotomy. So a neurosurgeon, or in Neuralink's case, their custom R1 robot, is drilling a coin-sized hole in the skull.
Wow.
They temporarily remove that piece of bone. The procedure is complex, it's long, and it requires a significant recovery time. Not to mention, all the risks that come with open brain surgery.
And the hardware they're actually placing directly into the brain tissue itself. It's almost impossibly delicate.
It's a materials science miracle, truly. The R1 robot is necessary because these components are just so fine. It implants these ultra-thin microelectrode threads.
How thin are we talking?
Just 4 to 6 micrometers wide. To give you some context, the average human hair is about 100 micrometers wide. So these threads are implanted directly into the cerebral cortex.
And that's where you get the best data.
That's where you get the highest fidelity data. That deep penetration is what it's all about.
So the whole design is engineered to deliver the maximum amount of data possible.
Precisely. The ambition is high-fidelity signal acquisition. Their current design is engineered for 124 electrode channels. They want to read the raw, granular neural activity, the firing of individual neurons.
And that level of access is what lets them dream so big, right? That's what fuels the science fiction level ambition.
Exactly. Their goals go way beyond just moving a cursor. They're chasing applications like telepathy, which they define as really complex, rapid mind-to-text communication, and even more audaciously, blind sight, where they aim to stimulate the visual cortex to create a kind of artificial vision for people who are blind. To do that, they believe they need thousands of channels deep inside the brain.
Okay, so now let's pivot completely. Let's go to path 2. Synchron's endovascular pragmatic play. This path is defined by just completely avoiding that surgical trauma.
They call their approach minimally invasive or semi-invasive. The key feature is that zero craniotomy is required. They use the body's own infrastructure, the neurovascular network, the blood vessels, as their highway into the brain.
That, to me, is the most amazing piece of engineering here. How do you get an electrical sensor next to the motor cortex using a blood vessel?
The device is called the Stentrode. It's a platinum electrode sensing device, but with just 16 electrodes, and they're embedded on this specialized nitinol stent scaffold.
Nitinol, that's that super elastic alloy you see in medical stents, right?
Exactly, and the fact that the electrodes are on a self-expanding scaffold is the key to the whole thing.
So how do they actually deploy it?
The surgical method is very similar to a standard neurovascular stenting procedure. They make a small incision, usually in the internal jugular vein in the neck.
In the neck, okay.
And the device, which is housed in a catheter, is threaded all the way up through the vascular system until it reaches the superior sagittal sinus, the SSS.
Wait, the superior sagittal sinus? That's one of the biggest veins that drains blood from the brain. Why there?
Because of its location, its anatomical proximity. The SSS is this large vessel that sits right up against the inner surface of the motor cortex.
Oh, okay.
So once the stentrode is delivered, the nitinol scaffold just self-expands. It conforms to the shape of the blood vessel, and it pushes those 16 electrodes firmly against the vessel wall.
Positioning them incredibly close to the neurons in the motor cortex?
Exactly. So they can record the signals through the vessel wall.
Okay, but that raises a huge question for me. If the electrodes are recording through the vessel wall and the dura and the cerebrospinal fluid, surely they're losing a ton of signal fidelity compared to Neuralink drilling right into the cortex. What's the trade-off there?
That is the necessary trade-off. It's a brilliant point. The signal Synchron captures is lower bandwidth. It's focused on the lower frequency macro-level signals associated with motor intent. We call them ECOG-like signals.
So they're not getting that single neuron firing that Neuralink is chasing.
No, they're not. But, and this is the key, the signals they do get are highly reliable and incredibly stable over the long term, precisely because they aren't causing any tissue damage. The stability and safety totally compensate for the lower data throughput.
And how much quicker is this procedure? That seems critical.
It is dramatically simpler. The median deployment time for the Stentrode device in the U.S. trials was recorded at only 20 minutes for the deployment itself.
20 minutes.
The total procedure time was around 4 hours. And critically, in their initial studies, 3 out of the 4 patients were discharged from the hospital within 48 hours.
Wow. Compare that to the recovery from open brain surgery.
It's night and day. And that simplification is the engine of their whole strategy. It's what makes them inherently scalable.
So once it's deployed, where does the brain data actually go?
The Stentrode is connected by this tiny lead that's tunneled under the skin down to what they call an implantable receiver transmitter unit, or IRTU. That unit sits in a little pocket just below the collarbone. And from that point, the data is transmitted wirelessly to a tablet or a computer using Bluetooth Low Energy.
So in pass 1, you have the maximalists drilling deep for raw high-res data. That's the Moonshot.
Right.
And in path 2, you have the pragmatists threading a device up a vein for reliable, scalable, low-trauma access. The pragmatic play.
That sets the stage perfectly for this compelling commercial and clinical battle.
In that battle, it seems to swing immediately in Synchron's favor when you start looking at the clinical validation data.
It does, especially on safety and long-term stability. The foundational proof for their whole approach came from what's called the SWIT-CH study, which was conducted in Australia.
Right. Let's get into that study. This was a first-in-human trial, right, involving patients with severe paralysis, mostly from ALS.
Yes, the initial group was 5 patients, with 4 of them making it into the final 12-month analysis. The primary goal, the primary endpoint, was safety, and the results were just critical for their future.
And what did they find?
They reported zero serious device-related adverse events during the entire 12-month follow-up period.
That's almost unheard of for a novel implantable neurotechnology. I mean, what specifically did they confirm was absent? Any complications?
Critically, they confirmed 0 blood vessel occlusion, so the stent didn't block the vein, and 0 device migration. The device stayed exactly where they put it, and the vessel stayed healthy for the full year.
That is the brass ring of stability for any long-term implant.
It is. And the study authors concluded that this endovascular access offers a favorable safety profile, but what that really means in practical terms is that they've de-risked the procedure itself in the eyes of regulators.
So they've proven it's feasible, and it's a less traumatic alternative to, well, every other major BCI tech that requires open brain surgery.
Exactly. And the signal quality itself, it averaged a usable 233 hertz bandwidth, and it stayed stable over that entire 12-month period. That's exactly what you need for chronic, reliable, everyday use.
Okay, so stability and safety are confirmed. But let's get to the question that everyone is probably asking. Can a 16-electrode array, which is orders of magnitude less complex than what Neuralink is building, can it actually provide useful, life-changing function?
And the key here is the strategic focus. The functionality is pragmatic. It's not superhuman. Their goal isn't to decode raw speech. It's the reliable generation of simple digital motor outputs, DMOs.
Which basically translates the thought of, say, clicking a mouse into a simple on-off switch.
Precisely, a basic digital switch output.
So give us some specifics. What kind of performance do they actually achieve?
The participants successfully controlled a computer using only their thoughts. The results showed typing speeds up to 14 correct characters per minute.
Just with motor imagery.
Purely using motor imagery. And crucially, they did this with accuracy rates that were consistently over 90%.
14 characters per minute. Now, if you can still use your hands, that sounds agonizingly slow. But if you're locked in or severely paralyzed from ALS, that speed it's the difference between total silence and having a voice again.
It is absolutely revolutionary for this population. The study carefully detailed how this restored their ability to perform what are called instrumental activities of daily living, or IADLs.
So real-world tasks.
Critical tasks. We're talking about hands-free texting to communicate with family, sending emails, online shopping, managing their own finances. The Stentrode system moves BCI from just a lab curiosity into a practical, viable tool that demonstrably improves their daily life.
So the low bandwidth trade-off, that 16-electrode constraint, it's basically mitigated by focusing on these pragmatic DMOs and that proven long-term longevity.
Yes. They solved the safety problem first and achieved functional utility. They focused on the regulatory, safety, and scalability challenges.
And because the procedure uses techniques that doctors already know.
Exactly. It leverages known interventional cardiology and neurology techniques. So the path to getting insurance coverage and scaling up to treat a wider population is so much clearer than for some novel, complex, open brain surgery. They achieved clinical translation while their competitors were still fighting for regulatory approval.
Okay, now let's look at the flip side of that. The inherent cost and complexity of Neuralink's Moonshot. Path 1 requires that direct cortical penetration, and that invasiveness brings with it these significant fundamental hurdles that Synchron just completely sidestepped.
The biological challenges are just unavoidable when you violate the blood-brain barrier and you insert foreign material directly into the cerebral cortex. The acute risks are immediate, localized inflammation, acute cell death.
And what happens over the long term? I mean, this device has to last for decades, ideally.
Long-term performance is defined by the body's defensive reaction. When you insert a microelectrode array, the immune response kicks in. You get this proliferation of glial cells. It's a process called reactive gliosis.
And that leads to the formation of a scar, right?
Yes, the notorious glial scar. It's a connective tissue sheath that forms around the electrode.
And how does that scar physically get in the way of the device's function?
The glial scar typically forms a barrier that's about 100 micrometers thick. And this fibrous capsule acts like an electrical insulator. It dramatically increases the impedance of the electrode.
So the electrodes just struggle to pick up the signals.
Exactly. The body is essentially building a physical shield around the foreign object, and that forces a chronic decline in signal quality over time.
So the very high performance that Neuralink is chasing comes with this built-in timer that's counting down on the viability of the implant itself.
That instability is the central technical challenge they have to overcome. And what's more, the brain itself isn't static. It moves relative to the skull during normal activities. We call this micromotion.
Right.
And if these fine, delicate electrode arrays are fixed to the skull, these tiny movements can cause constant friction against the brain tissue, leading to even more damage and signal degradation.
And this inherent instability, This is what caused friction with regulators from the very beginning, wasn't it?
Absolutely. You have to remember, the FDA initially rejected Neuralink's human trial application back in 2022, and the safety concerns they raised were highly specific and fundamental to the design.
What were the main sticking points the FDA highlighted?
They cited several critical issues. First, the complexity of the surgical implantation itself was a huge hurdle. Second, they had profound concerns over the safety of the device's lithium battery.
The battery inside the implant.
The battery powering the implant, yes. Third, they were worried about the potential for these ultra-flexible microelectrode wires to migrate within the brain tissue after implantation, which could cause all sorts of unforeseen damage.
And the really complex question,
Yeah.
what happens if the device fails and you have to take it out?
The difficulty and risk associated with explantation, the surgical removal, was paramount. I mean, these threads are inserted deep into sensitive brain tissue. Removing them without causing significant neurological damage poses an enormous ethical and logistical challenge. The FDA wanted proof that post-explantation care could be managed safely.
And that's much harder for an invasive device.
Much harder.
But despite those rejections, Neuralink did eventually get approval. They launched the PRIME study, and they implanted their first human patient, Nolan Arbaugh, in late 2023. What milestones did they report that showed the potential of this high-bandwidth approach?
They have certainly demonstrated very high potential. Nolan Arbaugh, who is paralyzed, was shown controlling a computer mouse just by thought, playing high-level chess, streaming his gameplay online.
And there was a second patient as well.
We heard reports of a second patient using the implant to design 3D objects, which is a really complex motor planning task. So this confirms that the N1 link can decode complex high-resolution motor intent far beyond simple DMOs.
But that inherent biological stability challenge, it seems to have shown up in that first patient almost immediately.
Unfortunately, yes. And it was a really serious setback. Neuralink reported that 85% of the implanted microelectrode threads retracted. They physically pulled back in Nolan Arbaugh shortly after the procedure.
Wow, 85%.
It's a dramatic, real-world example of this biological stability challenge. Now, they partially compensated for the signal loss with software recalibration, but it just vividly underscores that long-term struggle to maintain consistent performance.
Before we move on, we should acknowledge that the theoretical potential they're chasing, if they can solve the stability problem, it is astounding. We can't just dismiss the speed they're aiming for.
That's a vital piece of context.
Right.
While Synchron's 14 characters per minute is life-changing, other high-end, research-focused BCI systems have achieved truly transformative speeds.
Right.
We've seen reports of advanced speech decoding systems, often using ECOG arrays placed on the brain's surface, that have achieved speeds of up to 21 words per minute. That's almost conversational pace.
And that's the level Neuralink is striving for.
That's the transformative goal. They're aiming for true neuroprosthetic restoration of speech, and that requires massive data throughput from the speech network itself.
So Neuralink is aiming for this neurological transformation, but Synchron is currently leading the race for clinical restoration by putting safety and stability first.
And that lead in clinical translation has now turned into a massive strategic advantage in the commercial world. If the first parts of our discussion were about engineering risks, this next part is about market domination. And here, Synchron has secured a crucial victory: native integration with Apple.
Okay, let's look closely at this. Synchron became the very first BCI company to achieve native integration with Apple's core operating systems, iOS, iPadOS, and visionOS. How does this BCI Human Interface Device Protocol, the BCI HID, shift the balance of power?
This is a fundamental, market-defining victory. By working with Apple to define this protocol, Synchron has elevated brain signals to the status of a native first-class input within the world's most dominant consumer tech ecosystem.
So a brain signal is no longer some niche medical output. It's now standardized, just like touch or voice or typing.
Exactly. And that standardization is key. It positions Synchron to be the default BCI provider for millions of Apple users who rely on accessibility features.
And it creates a huge barrier to entry for their competitors.
A massive one. Think about it. Competitors like Neuralink now have to adapt their complex proprietary hardware to conform to a standard that was largely defined by their main rival and the world's biggest tech company. Synchron's system just interfaces directly with Apple's built-in accessibility features, like switch control.
So a user with a Stentrode can just use their thoughts to navigate their iPhone. right out of the box.
Seamlessly, yes. Make selections, perform complex tasks. It just works.
And this BCI HID protocol isn't just about sending simple clicks, is it? It seems to pave the way for something much more sophisticated.
Yes, and this is where the AI and the closed-loop future really come in. The protocol is designed to be bidirectional. It enables closed-loop communication.
Meaning the device doesn't just send commands out from the brain.
Right. The operating system, the iPhone or iPad, can transmit contextual information back to the BCI system.
Give me an example of how that would work in practice.
Okay, so imagine the user is trying to select a specific icon on a really cluttered screen. The system can send data back to the BCI decoder, indicating, say, the proximity of other icons, or maybe highlighting which area of the screen the user is currently looking at.
So the BCI software can dynamically adjust its interpretation.
Constantly. It enhances accuracy and reduces latency. It's like the software is asking the user's thought process, are you trying to click send or are you trying to click delete?
It sounds like they're using software and AI to completely overcome the hardware limitations of having only 16 channels. How else are they using AI to maximize function?
Their AI strategy is totally focused on squeezing every last piece of actionable intent out of those 16 stable channels. They're developing a proprietary technology they call chiral. They call it a brain foundational model.
What does a brain foundational model even mean? Is this similar to how a large language model works?
It operates on a similar principle, the idea of pre-training. Traditional decoding models are linear. They need a lot of recalibration for every new user. Chiral uses generative pre-training on huge data sets of existing brainwave patterns to develop this baseline understanding of how human intent generally translates into electrical signals.
So the AI is essentially learning to understand brainwaves more deeply.
Exactly. It makes the decoding process faster, more robust to noise, and immediately more accurate for new users.
And to handle the speed you'd need for real-time interaction, they had to partner with a major player in high-speed computing.
That's right. Synchron is leveraging NVIDIA's ecosystem, specifically their Holoscan platform. This is critical because BCI requires extremely low latency. If you think click and the cursor moves a quarter of a second later, the whole experience is ruined.
Right? It's unusable.
By leveraging NVIDIA's edge AI processing, they can run those sophisticated chiral algorithms in real time right on the external controller, ensuring the user feels this seamless, instant connection between thought and action.
And that combination of strategic moves, safety, and AI innovation is clearly resonating with the financial world.
Oh, absolutely. Synchron secured a massive $200 million Series D funding round in late 2025. This shows deep investor confidence.
They see a predictable path to market.
A predictable, scalable path to market precisely because of the low trauma procedure and the clear regulatory advantage. Investors are betting that scalability and safety, backed by smart AI, will win the market, not just maximal data throughput.
It's a very clean-cut strategy. Secure the infrastructure, standardize the input, and then use sophisticated AI to make a safe, scalable device functionally excellent.
And this profound divergence in technique and ambition, it naturally leads us into the critical ethical and philosophical questions around all of this. The implantation approach fundamentally dictates the ethical profile of the device.
So let's compare the ethical footprints of the two systems.
Synchron's endovascular approach. Because it avoids the craniotomy and it uses a well-established vascular procedure, it just inherently carries a lower ethical burden when it comes to surgical risk.
So it's ethically viable for a much broader range of applications.
And it's simpler for regulatory bodies to manage, since the risks are comparable to existing approved procedures.
But the extreme invasiveness of Neuralink's approach, that requires massive ethical justification, massive safeguards.
Indeed. It necessitates stringent safeguards covering a whole range of concerns: chronic infection, inflammation, iatrogenic damage harm caused by the intervention itself. But the most complex issues revolve around maintenance and reversibility.
Taking it out.
Exactly. The greater the invasiveness, the more difficult post-explantation care becomes, especially when you're dealing with potentially damaged or scarred brain tissue. The long-term permanence of a device like that raises huge questions of medical accountability decades down the line.
And the ultimate ethical frontier, though, this applies to all devices that record raw thought, the privacy and security of neural data, the potential for misuse,
That is the paramount concern as we enter this era of commercialized thought recording. The data recorded directly from your brain is infinitely more sensitive than your location data or your browsing history.
It has to be protected like genetic information.
At a minimum, if this neural data, your raw intentions, your emotional states, your latent thoughts, if that's commodified or exposed, the societal risk is immense.
And it goes beyond just privacy breaches, right? What are the risks of hacking and misuse of this information?
The risk is twofold. First, a security failure could expose deeply personal cognitive data, leading to unprecedented psychological and financial harm. But second, and perhaps more worryingly for the future, is the risk to personal autonomy.
How so?
Devices that not only record but are capable of stimulating cortical tissue raise the question of control. There's a very real possibility that external stimuli, maybe delivered through the BCI, could influence or even alter a user's voluntary choices, thoughts, or decisions.
So it can manipulate human intent.
The potential is there, and that is a massive ethical red line.
We also have to consider distributive justice. How do we make sure this life-changing technology is accessible to everyone who needs it?
Right. If BCI becomes a necessity for communication, we cannot let it create a societal divide where only the wealthy can afford this kind of restoration. Regulators have to ensure that cost, insurance coverage, and accessibility are addressed early on.
This whole philosophical discussion brings us to a remarkable piece of research that was in our sources that might just fundamentally challenge the entire rationale behind the high-bandwidth moonshot.
This finding is truly mind-bending because it imposes a physical constraint on this whole race. Research suggests that the overall human behavior output rate, the combined speed of processing perception, formulating an action, and executing a thought, is biologically constrained.
To what?
To approximately 10 bits per second.
10 bits per second. To put that in perspective for you, we are talking about data transfer rates thousands of times slower than the old dial-up modems we used 30 years ago. It's like a slow telegraph operator.
Exactly. I mean, we know sensory input like the optic nerve can transfer data incredibly fast, maybe 10 million bits per second. But when that data is processed, aggregated, filtered, and ultimately synthesized into a conscious thought or a motor command, the bottleneck appears to be massive. The conscious output is severely constrained.
So if that inherent biological limitation of 10 bits per second is accurate, doesn't that just fundamentally undermine the entire necessity of pursuing an ultra-high bandwidth interface with the 3024 channels like Neuralink is focused on?
It absolutely strengthens the argument for the pragmatic approach. Why endure the immense risk of a craniotomy, of inflammation, of potential device degradation for a theoretical 1024 channels when the user's own cognitive output might be physically limited to using only a tiny fraction of that capacity?
It completely bolsters the case for stable, pragmatic BCI solutions like the Stentrode.
Right. Solutions that prioritize reliability and longevity within the biological constraints of human action, rather than just pursuing some superhuman speed that the brain can't even effectively use.
It reframes the entire competition. It turns the race from who can build the biggest pipe to who can build the safest, most reliable tool that delivers exactly the small amount of data the human brain can actually produce.
Precisely. And in that context, the safety and commercial advantages Synchron holds become even more critical because they are meeting a human need with a technology that aligns with human neurological reality, not just with engineering ambition.
Okay, let's unpack this entire deep dive. The modern BCI race is definitively crystallized in this competition. It's two technological philosophies. On one side, you have Neuralink, championing the high-risk pursuit of maximum performance.
And on the other, you see Synchron, leading with this commercially advanced focus on safety, rapid clinical validation, and immediate translational maturity.
But what's truly fascinating here, what defines the current market leadership, is Synchron's strategic move to define that BCI HID protocol with Apple.
It establishes brain signals as a foundational input layer for consumer technology globally. And that shift forces a fundamental and immediate reconsideration of how we interact with the digital world. It moves BCI from a theoretical medical device to a commercial standard.
So the era of mind-reading AI is no longer some future prospect. It's here. And it's being driven not just by raw science, but by strategic safety, scalability, and commercial dominance.
Indeed. The competition is not for who can collect the most data, but who can safely deliver a predictable, long-term solution to the millions who desperately need to regain their connection to the world. A solution that is predictable enough for both insurers and regulators.
So as you move through your day, controlling your devices with the touch of a finger or the sound of your voice, consider this final provocative thought for yourself. Now that a brain signal is officially a commercialized digital input used for texting, shopping, and navigating digital environments, what specific new legal precedents and policy safeguards must governments and regulatory bodies create right now to protect the integrity, privacy, and autonomy of the raw neural data transmitted from within your own skull? What are the policy risks we are overlooking in the pursuit of thought control?